Welcome back. We're still working on analyzing voltaic cells, and this is what a typical question can look like, where they just say, here's a bunch of chemical species, we put them all in a bowl, tell us what's going to happen when they start reacting, if they start reacting. So you start by making a list of all the players that are in this environment. We have graphite, which is carbon, more about that in a minute. In an acidified, if Chem 20 is fresh in your mind, you'll know that acidic means full of hydrogen ions. If you didn't know that, you know it now. Potassium dichromate solution. That's an ionic compound. It dissolves into potassium ions and dichromate ions. We have an iron electrode, iron metal, and iron 2 sulfate. Iron 2 and sulfate ions. And since these things are in solution, we can assume we have water as well. Often the water doesn't do anything, but sometimes it does, so it's good to have it on your list. So these are all the things that could react in our cell, and armed with that, we make our way over to the redox table in the data book. And that list didn't come along with me, which is inconvenient. So we have to remember as we're going down this list that we're looking for, what was there? Carbon, acid dichromate. So we had K plus Cr2O7. We had iron metal, iron 2, sulfate ions, and water. So we're going to be reading down the redox table looking for any of these things, and whatever we find first is our strongest oxidizer. So this goes fluorine, no, not on our list. That's not going to do anything in this solution. Lead oxide, don't have that. Permanganate, nope. Gold, nope. Perchlorate, no. Chlorine, no. HNO2, no. Dichromate and hydrogen, yes. This, acid dichromate, those two things working together are our strongest oxidizing agent. So one of the reactions we get in this cell is going to be, one of the half reactions in this cell is going to be Cr2O7 and 14 hydrogens doing this, turning into chromium ions and water. So good, that takes care of our strongest oxidizer. Now we go to the bottom right corner of the redox table and we start reading up, looking for our strongest reducer. Lithium, nope, our cell doesn't have that. Potassium, we have potassium ions. We do not have potassium metal. They're very different things, so that's a no. Barium, nope, 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 nope. We have SO4. This is SO3, not the same. Selenium, nope. Chromium. We have dichromate, but this is not even close. We have hydrogen ions. That's not the same as hydrogen. Zinc, nope. Silver, nope, nope. Iron. Iron metal, right there, is going to be our strongest reducing agent. And because this reaction is starting with the iron metal, it has to go in reverse. It has to go this way. So we're going to go from iron to iron 2 plus 2 electrons. So now that we have those two reactions, I just want to look at the dichromate one, 14627. Okay. Now we can get back here and take down the two half reactions. So one of them is Cr2O72 minus 14 hydrogen plus 6 electrons gives 2 dichromates and 7 water. You copy that out of the data book. This is the 14627 I was trying to hold in my head. And our reducing agent was iron metal. That reaction goes in reverse relative to what's in the data book, so we get iron turning into iron 2 and 2 electrons. So those are the two reactions we'd have in our cell. Now, they ask us we're supposed to answer a bunch of questions about these, like which one's the cathode, which is the anode, and so on. So let's rough that out real fast. So we'd have our two containers, salt bridge connecting that, bar over here, wire connecting the bars, liquid, liquid. Pretty much all cells look like this. On one side of this, we're going to have the reaction Cr2O7 plus 14 hydrogens turns into chrome 3 and water. So there's a solution here that'll have our Cr2O7. That's an ion, so it has to be in solution. It's got to be down in the liquid. The hydrogen ions, same thing. They'll be down in solution. And this reaction is taking in electrons. So the electrons have to be flowing into here to keep this reaction going. That tells us the electrons are flowing into the dichromate side of the cell. My electrons are going to be flowing right to left. Nothing solid forms in this cell. A lot of our cells produce a solid product and then it plates onto the electrode, but that's not happening here. We have ions, 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 and liquid water. So we're just going to have some kind of ion in the liquid turning into different ions in the liquid. That's not as fun as some of our reactions, but that's what's happening here. On the other side of this reaction, we have iron metal turning into iron ions. So this bar would have to be made of solid iron, and it's going to be dissolving and releasing iron 2 ions into the solution. If we're losing iron metal, that means this bar is going to be dissolving and shrinking as metal gets eaten away and turned into dissolved ions. So the ions are going to pile up here and the metal is going to slowly disappear. This reaction releases electrons, it says. Iron metal turns into ions that float out here, and electrons which flow out. So again, that makes sense that electrons are going to come out of this electrode and flow over to the dichromate side where they're wanted. As positive ions come out of here, the right side is going to fill up with more and more positive ions. So what is that going to mean for flow? If the right side's getting more and more positive, all these positive charges look at each other and go, ugh, positives. I hate positives. Positive charges repel each other, so to try to get away from each other, they're going to start flowing up into the salt bridge. And positive ions are going to flow this way, and this way, and this way. Hydrogen ions that see positives starting to flow through here are going to go ugh and start moving towards the electrode. So we'd expect to see positive ions flowing right to left. If you ran this cell for minutes or hours, you'd start to see positive ions, or what we call cations, flowing increasingly towards the left side. And negative ions would go in the opposite direction. So dichromate is going to be attracted and start pulling towards the right side because there's more and more positive over here. Negative ions are attracted to positive ions and will go the other way. And one of the last things they ask about, which side of this is the cathode and which side of this is the anode? When we went to the redox table, we found that acid dichromate was our strongest oxidizing agent. Now, that means it oxidizes the other thing. That means our iron must be getting oxidized. If you oxidize other people, then you are getting reduced. Okay, so if you're the strongest oxidizer, you oxidize the other thing, you get reduced. So the reaction that happens to you is a reduction. If you're the strongest reducing agent, you reduce the other guy. Here we are. But you get oxidized. What happens to you is an oxidation. Reduction has the letter C in it, so that happens at the cathode. Oxidation has the letter A in it, so that one happens at the anode. This dichromate reaction is going to happen at our cathode, and the iron reaction is the one at the anode. Makes sense that positive ions will flow this way. We know that These positives, cations, flow towards the cathode. That's what they were doing. Negative ions, like Cr2O7, will flow this way. They're called anions. They flow towards the anode. I know that's a lot of different ways to remember these things, and I'm kind of using a lot of different ones on purpose. I hope you find something in there that you like, that you can use consistently. Pick your favorite way and just kind of ignore the others. You don't need to know 3 ways to do everything. But there are a lot of connections in here, so just pick your favorites.